Okay. All right. Let's start presenting. Cool, cool. All right, so here we are. All right, homework 0 is due on Sunday at 11:59 p.m. As I mentioned to you guys, the way I've set it up, we release homeworks Mondays in the afternoon, around 5 is what I'm trying to aim for. They are then due Sunday at 11:59. If you have feedback on maybe trying to adjust this schedule, maybe Sundays don't work for you, I am happy to do so. We will try to figure out something that does work for you. For homework 0, if you have not started, you should probably start. It is the easiest homework in this class, and it is also worth 3.63% of your final grade. So it should be like a free 4% points in your final grade. Like it does not cover anything technical, and it is mostly graded on completion. So it's just to get you set up on the course tools, okay? So please, like get that done as soon as you can. It is not meant to be difficult. It is meant to be, I don't know. I actually noticed a couple of people already submitted homework. You guys probably felt it was just like way too easy and covered nothing. Or actually, I don't know. Well, how did you guys feel about homework 0? Who already submitted it? Got a couple of folks. What were your thoughts on homework 0? Yeah, so not time consuming, not difficult as long as you do it. All right, so if you haven't gotten started, please get that done. Please don't leave it to the last minute. I have already run into some technical issues with people, PDFs not being uploaded, random stuff. Email me. The sooner you know, and the sooner you let me know, the sooner I can fix it. Feel free to talk. Like a couple of students have already emailed me. I usually try to fix things like, within an hour of when you let me know. But if you're going to let me know at, 10 p.m. on Sunday, that's going to be a little awkward for us, right? All right. Homework 1 is going to be released on Monday. I am still preparing it. This is going to be your first homework that has a coding component to it in C++. So for this homework, I know Monday we don't have lecture. The homework is going to be released anyway in the afternoon. If you can, please try to get started on it as early in the week as possible, because this is the first time there's coding. And this is not necessarily because I think the homework is going to be difficult for you, but if there are any issues or bugs on my end as to how to submit it, how to run the code, again, the earlier I know, the earlier you run into the issues, and the earlier I know, the faster I can fix them so that you can actually submit your homework. So please, if you can get started as soon as it comes out on Monday, just trying it out. You don't even have to finish it, but just trying out everything that we're setting up, that would be great. Again, reminder, comp285.ml, that's our course website. All the information is going to be there: lectures, slides, homework assignments, additional resources. Cool. All right, so welcome. Lecture 2, we're going to be covering correctness and running time of one sorting algorithm in this lecture. I did ask last lecture if you guys were familiar with merge sort, so I am considering putting some content on the homework that covers divide and conquer with a modified version of merge sort. How comfortable do people feel with merge sort? Okay, I'm seeing a thumbs down. Oh, some thumbs down. Iffy. Okay, we'll see. So we are not covering merge sort today. We are going to be covering something else. But anyway, recall what we have accomplished. So first lecture, we covered why algorithms are awesome. There are 3 main questions when designing an algorithm. These are 3 questions you should think about when people are asking you algorithm questions in a coding interview. Does it work? Step 1, we got to figure out if the algorithm is doing what we want it to do. How fast is it? Is the second question you should try to answer once you have a solution, right? What's the big O for it? And then, can I do better? And then you basically repeat this until you find better solutions, all right? Technical stuff that we covered last lecture, caret suba for integer multiplication. This is a divide and conquer algorithm. You guys should probably be familiar with that. And then we did a lot of hand wavy stuff about how many operations it's going to take. So in today's lecture, we're going to be a little bit more formal. So we're going to introduce a little bit more, I guess, formality. I found this picture on Google Pictures. To both of these questions, like whether it works and how fast it is. We're going to do that in more detail for a slightly simpler algorithm than Karatsuba, so that we can focus on the proving part of it and on the big O part of it, right? Before that, everyone say hello to Chi Wang. She's here. She is our one TA so far for the course. I am trying to find more because there's a lot of you and I want you to be well supported, but I'm sure Chi is going to do a great job. She, I don't know if you want to do, if you want to say something to the class now or. Yeah, she actually took this class last semester, so she knows a lot of the content we're covering and it's fresh in her mind, so she can definitely help you guys out. All right, so big questions today. We're going to cover how to sort, what happens in the worst case, and then we're going to cover what happens in the asymptotic case. All right, so these are the new concepts we're introducing in this lecture. Hopefully, this algorithm is a review for you. We'll cover it because sorting is very important. It shows up everywhere. Okay, so even in my job, I have written and used sorting algorithms that are slightly modified. So the algorithms we cover are going to be on a single computer, fairly basic. Normally, what will happen is when you go to a place like Google or Facebook or other large companies, you will implement the same sorting algorithm, but you'll have to figure out how to do it across many different computers and many different machines. So merge sort is actually a very good algorithm for distributed training, because you can imagine that as you split it up, instead of just splitting it in your computer memory in one computer, you can actually take each of the pieces and send it to a different computer to do the work. Okay, and that's how you can scale to like, hey, I want to sort, 1 billion Google search results. How do I do that? You actually use merge sort in a very more complicated way, but it's essentially the same algorithm. Yeah, this will be useful to learn how to formally think as to whether an algorithm is correct and the runtime. So this is so sorting, right? So here's an example list, and then when you sort it, it looks like this, right? So it's everyone. So if I wanted to check for whether a list is sorted, how would I go about doing that? So I am not asking you to sort a list. I'm asking you, I give you a list of elements. Let's say I give you a vector, and I want to check, is this vector sorted? Okay. So I got one answer. Somebody said iterate over the list. So have some sort of for loop, right? That goes over each element in the vector and the list, whatever you're working with. And he's saying, I'm going to compare elements that are next to each other. So I'm going to compare 1 and 2. And what am I going to check? Yeah. So for a list to be sorted, so the thing you guys have to remember, if a list is sorted is just, it means that the elements are not, if let's say we're sorting in increasing order, it means that the elements do not decrease, right? So you can write a very simple algorithm that just checks, is 1 bigger than 2? If it is, then my list is not sorted, right? And then I continue, is 2 bigger than 3? If it is, then my list is not sorted, right? And essentially, I keep doing this check. If it never succeeds, then my list is sorted. Like if I get to the end of it and I never found a pair of numbers where this number was bigger than the next one, then the list is sorted. That makes sense? So we're actually going to see that in code today. But actually, another class exercise for some of those people out there that love coding. This is C++ to get you guys introduced. And what is this algorithm? What is it doing? Oh, yeah. Checking to see if the list is sorted. Good guess based on what I just said in lecture. That is not what it is doing, however. Yeah, back there. actually sorting the list. Yes, yes, that is a good answer back there. So this is one implementation of an algorithm that sorts the list. How to explain it? This one's actually a little difficult to explain. And I will tell you as well, when I wrote this code and then I looked at it afterwards, it took me a while to remember what it was doing. So it is not unheard of to not understand what it's doing, but essentially it's given a vector of elements at the top. Then it creates a new vector, which is empty to start with. All right. Then it iterates. So this is a for loop iterating over our elements that were given. So for each element in the vector, it creates another for loop that iterates over this vector plus 1. Okay. So the first iteration of this for loop is actually only going to go once because the sorted vector is of size 0 to begin with, right? So in the first iteration, if the iteration is equal to the size or the sorted element at the ith position is greater than the element I'm looking at, then it is going to put that element into the sorted vector, and it's going to do a whole bunch of other stuff. Anyway, that's one implementation. We will actually walk through this algorithm in detail for the rest of the lecture. So if you don't get it yet, that's fine. But what about this one? What does this algorithm do? Again, if you don't get it, that's fine, because we're actually going to walk through it in lecture. But any guesses? This one's actually a little simpler. Not simpler, it's a little easier to read than the last one. Yeah. Okay, so does it check if good guess. In a way, sort of, but that is not the final thing that it is doing. This is actually also sorting. Oh, yeah, sorry. Yeah, so this is also sorting the elements here, but you'll notice it is sorting it in place. So it is actually the same algorithm. So the key thing to remember here is these two algorithms are actually the same. It's just written in two different ways. So again, this is also why we can tell you cheat when you like copy paste code, because even if I give you the same problem, you can imagine the ways to write it can be very different. All right. So these are actually doing the exact same thing, both of the algorithms. They're actually both insertion sort. So who remembers insertion sort from maybe their last lecture, or like not last lecture, but last class, Comp 280? A little bit. So actually, both of those algorithms, what they're doing is an implementation in C++ of the algorithm insertion sort. All right, so we're going to cover insertion sort. And let's do an example. So this is going to tell you exactly what the code was doing for both implementations. So if you had difficulty figuring out what the code was doing, we will cover in an example what it should be doing. And then you can go back and sort of look at the code and say like, oh, is it actually doing this? Okay. So for insertion sort, the way it works is we start by moving the second element in our list towards the beginning of the list, okay? Until I find something that is smaller than it, or you can't go any further. So what that means is here, I look at 4, this is my element, and I compare it towards the beginning of my list. I compare it to 6. If it's smaller, I'm gonna move the 4 to be before the 6. Once I get to the end, I'm done. Right, that's like one interior step of the insertion sort algorithm. So the reason it's called insertion sort is because what you do next is now you look at the next element. So you look at element 3 and you try to insert it into the beginning of the list, the beginning part, right? So here 3, I compare to 6 and I say, oh, 3 is smaller. So actually 3 should go, these should be switched, right? So it should be 4, 3, 6. Then I compare 3 and I look at 4 and I say, oh, 3 is smaller. So these should be switched. right? So I end with 3, 4, 6, right? What's the next step? Who can walk me through it? Hey, actually, let's see. Someone else in the class I saw. Is that Trinity or yeah? Exactly. You repeat the same thing. So this is why we have 2 for loops. If you remember in the code that we had before, we actually had 2 for loops in the first one. So the first one actually had 2 for loops. Okay. The second one had a for loop and a while loop. So that's the 2 loops. Okay. And Trinity is perfectly right. You look at 8 and you notice that 8 is not bigger than 6. So it is already in the right place. So you finish. You're done. And then for the last step, you look at 5 and you do the same thing. Each time you say, okay, you're inserting it into an already sorted list, right? So that's why it's called insertion sort, right? You look at one element and you try to insert it into its right position, right? This is probably similar to what you would do if you had like, I don't know if you guys play poker or something, but you get like all your cards and you like pick one out and you try to like insert it into the right place so that it's like sorted in a way. So you have like, 1, 2, 3, and you have like all the hearts together and all the whatever together. So that's the exact same algorithm that we're doing here, but we're doing it with numbers. So now again, like our guiding questions are, does this algorithm work and how fast is it? So does it work? Yes. Actually, the first question you should ask is like, what exactly does that mean when I ask if something works and how fast is it? So that's what we're going to be covering here. So in this class, when we ask if something works, we're asking, does it work in the worst case? Okay. So my claim is that insertion sort works. And my proof that I'm giving to you is that it worked in this example. Therefore, the algorithm I described to you, that is like take an element and then compare it to all the previous elements, insert it as long as you get to like a number that's not smaller than it. That algorithm always sorts lists. And my proof is we just walked through one example, therefore it works. Who accepts this proof? We have, yeah, if you think this is a sufficient proof, raise your hand. 2, 3. Okay, we have 2 people. Okay, it's actually not sufficient. So here's something even better, okay? I know it works because I wrote a program that, I actually wrote this code. So let's see if I remember where I wrote it. Okay, I think I have the link somewhere. Okay, I lost the link. So C++ online compiler. Okay. So yeah, there we go. So I actually wrote the code. So actually the code you saw on the screen is working C++ code. So you can actually copy paste it, it works. I wrote both of the algorithms. And then I wrote this function that essentially takes this vector, shuffles it, and then sorts it using my algorithms. And then I wrote this function. If you guys remember, I asked you, how would you check if something is sorted? This is the function in C++ that I think one of you described to me to check if something is sorted, right? So I iterate over the input, and then I check the elements next to each other. If ever the element before is bigger than the element after, then it is not sorted. So I return false. If I get through all those checks, so if I finish the for loop, I return true. So anyway, I tried it, and I can actually run it here. So you can run the code on this online editor, and it does it for like 100 different arrays. And it tells me that yes, each and every single one of them is sorted. So is this enough proof? Are you convinced that this algorithm works? Okay, you guys are convinced because it does work, but you shouldn't be convinced, okay? Because in general, it is not enough for it to work on a single input, okay? There could be edge cases. Somebody should have asked me to try it on an empty array and see if my algorithm worked, right? Which it should, because it should return empty, but you never know. Maybe I have a bug and it just crashes the program, right? It is not enough that it works on most inputs, okay? So just because I tried it on 100, do you know how many different arrays there are in the world? It's like actually infinite, right? So it is not enough to know that it works on most inputs. What we will use in this class is we will do worst case analysis. So we will use logic to walk through the algorithm to prove mathematically that it always works, no matter what the input is, okay? Yeah. So worst case analysis, so this is the way you think about worst case analysis. So anytime you're designing an algorithm, you are the algorithm designer. So you're the one writing the code, you're the one thinking of the solution. So you're gonna propose an algorithm, and what's gonna happen is you need to think someone is gonna come, they're gonna look at my code, they're gonna see what I wrote, and they will give you an input that is the worst possible for your algorithm, all right? And this actually matters when you're working at the scale of Meta or Google or like DeepMind or whatever. Like I have personally had cases where you have to write algorithms that handle the worst possible input that the user is going to give you. And this is not even for algorithms, this is just for coding, because they're like, users always mess up in some way, and they will give you the weirdest input to the code that you write. So you need to be able to handle these like edge cases. And that's not even considering the fact that there are people that are actively trying to break your code at most companies, right? So Google, right, for example, there are literally like probably thousands of quote unquote hackers around the world constantly trying to figure out how to break into Google's code, right? Same with Meta, same with Facebook. So you do need to generally think about like the worst case. So going back to insertion work, how does it work? So it's a pretty simple algorithm. So you guys are probably a little bit bored. Future algorithms that we cover in class are not going to be as simple. So you need to get a little bit familiar with how to think through more rigorously. We're going to use this example in lecture because I didn't want to introduce a new algorithm to you. I just wanted to focus on how do we prove that an algorithm works. So we sort of already did this. And I think here's like the key to why insertion sort works, right? So if we already have a sorted list, 3, 4, 6, 8, right? And we want to add a new element to it, it's pretty obvious to us that if we follow the process that we described, where it's like, here's the new element, let me compare it to 8. Okay, it's smaller. Let me compare it to 6. Okay, it's smaller. Let me compare it to 4. Oh, it's bigger. Okay, it goes between 4 and 6, right? It's pretty obvious that if I have a sorted list, by following this process, I will end up with a sorted list, right? So yeah, we insert 5 right after the largest thing that's still smaller than it, aka right after 4, okay? And this is actually what we do at each single step of the algorithm, right? So you can see that for this example, again, at the very beginning, the first element, 6, if you forget about the rest of this is a sorted list already, right? A single element is always already sorted. So we can say what we're doing is we're trying to insert 4 into a list that's already sorted. And that obviously works based on the process that we described, right? So now the next step, we know that 4 and 6, we know this is sorted, right? So we can think again, okay, now we're trying to insert 3 into an already sorted list. Therefore, it works. And you can imagine like at each step, this is what you're repeating, and that's why the algorithm works, right? So I'm walking you through an example, but in general, this is actually something that's very well set up for a proof by induction. How many people in the class have heard about proofs by induction? Oh, actually quite a few. Oh, great. Are you guys like math majors? Where do you learn proof by induction? Is it like other CS classes or? Yeah, and anyone, where did you learn proof by induction? Oh, a little bit in calculus. Okay, comp 20. I heard somebody. 180 also. Oh, okay, great. Oh, okay. So I thought this was going to be hard, but maybe this is kind of okay. So maybe you guys can give me feedback at the end of the lecture that you already know all this stuff. Huh? Oh, you've heard of it. Okay. All right. Well, we're going to cover it in a little bit more detail, but again, don't worry. I actually didn't even know proofs by induction existed until my sophomore year when I took my data structures and algorithms class. They're actually not that hard, and actually, you just did one. I just didn't tell you that's what it was. So all the details are going to be in the lecture notes, like detailed, like mathematical symbol proofs, etc. So you're welcome to take a look at that. In lecture, I will only give you the outlines. So here's generally, there's a couple of different components to a proof by induction. All right, so the first component is you have to define what is called your hypothesis. Like what is the key to move from element I to element I plus 1? So in our case, our hypothesis is that if my array is sorted all the way from 0, this means from 0 to I plus 1, then at the end of the ith iteration, once I've iterated I times through my algorithm of the outer loop, or my inductive hypothesis is that it is sorted after the ith iteration. So after I've done I iterations of my algorithm, this part of the array is sorted. Okay. Then you cover your base case. So what happens when I equals 0, right? So for every proof by induction, you need these pieces. You have an inductive hypothesis and you have a base case. So the base case, if you plug in I equals 0, this says my array from 0 to 1 is sorted at the end of the 0th iteration. So this is saying at the beginning of my algorithm, the first element in my array is sorted. Everybody agree with that? Is that true? Is that obvious to you guys that if I have just a single element in the list, it is sorted? Okay, cool. That's my base case. And then what we do is we get a little bit trickier. We look at the inductive step. So we say, forget about specific examples, all right? My inductive hypothesis is going to be that for some I equal to k minus 1, so again, this is just the letter. So I'm just throwing in a letter. For some iteration, if this statement holds for the previous iteration, right? So if it is true one step before, then it is true one step after, right? And this is the part that you actually need to prove. So it's like in one step of the algorithm, it is true that before it was sorted, and then after one more element is now sorted. All right. And yeah, I basically summarized it there. And we sort of argued, so I didn't go in detail here, but that's what we argued when we were talking about, like, if I already have a sorted list and I put one element into it, it'll be sorted, right? So this is just saying like, oh, instead of starting at 0, instead of starting at 1, let's start at some arbitrary k. Let's assume everything up to k minus 1 is already sorted. If I add one more element, if I do one more iteration of my algorithm, everything up to k is going to be sorted, right? The conclusion is that the inductive hypothesis holds for 0 to n minus 1. In particular, it holds for I equals n minus 1, which means at the end of the iterations for my algorithm, everything is sorted from A to the nth index, which is the entire array. So this is like, so I guess like something to introduce, like I said, this is a more rigorous version of the proof. For this algorithm, you guys are probably like, okay, this is just like too much detail that we're going into. And like, it's obvious insertion sort works for me, right? Who's basically like, you're basically repeating the same thing over and over again. Anyone thinking? No. Okay, so a lot of this is new. Okay, that's great because this is one of the simpler proofs for induction, right? It should seem like a lot of this makes sense. But I want to introduce you guys to this process because for some of the more difficult algorithms, it is not going to be as obvious that they work. and you want to try to think of like, how do I prove that they work? And if you have this framework, it's a lot easier because you can say, okay, I need to prove it for one case, for the base case. So what is the simplest example where my algorithm works? Well, the simplest one is when I have just one element in the array. Of course it works, okay? Then you need to prove it for, let's assume it works up to a certain point. What about my algorithm makes it so that it also works if I take one more step, right? That's the things with inductive proofs, okay? Like I said, I'll provide the details in lecture notes. I probably won't test you on this, but this is how you normally try to think through algorithms, and it will help you, I guess, when you're doing interview questions. If you ever have an algorithm and somebody asks you, does this work? You can try to jump to this framework, which is like, well, it works for the case when it's 0. And if I already have part of the solution, when it does one more step, it still works, right? So now big questions, we're going to cover asymptotic cases. Any questions on like why insertion sort works? Did you guys follow along? Yeah. What about like inductive proofs? How comfortable do you guys feel about like, you know, if I asked you this on a homework assignment and I told you, give me the base case, give me the inductive step, give me the conclusion. Is that thumbs down? Okay, not that great. Okay, so we might cover it a little bit more, or I will try to walk you step by step. But anyway, back to insertion sort, we're going to like, how fast is it? That's the second question we want to answer for any algorithm. How fast is it? So like I told you, the first thing we can do, and everybody has suggested this. Oh, I guess this is the link to the code. It's on the slides, so if you want to go check it out, you can run it. How fast is it? You could just code it up and then you could time it, right? You could try it for bigger and bigger inputs and then, you know, measure how many milliseconds it takes. Here are the two versions of the same algorithm. So it's the same algorithm, just implemented in two different ways. The first implementation is pretty bad. So it's a lot slower. And the second implementation is also, it's good, but it's not the best possible, but it's better, right? So the problem with this is that it's the same algorithm, but it can be slower or faster depending on what computer you're on. It can be slower or faster depending on how you wrote it, right? It does the same thing. Both algorithms do the same thing. They follow the same steps. If you look at the code, they're actually both doing the same thing where they're like, let me look at one element and then move it along to see where it fits. Let me look at the next one, move it along, see where it fits. Both pieces of code I shared with you at the beginning of lecture are doing that. They're just doing it in different ways. And one of them is a lot slower than the other. So that's actually not a very good way of measuring how fast an algorithm is for the purposes of designing an algorithm. So last time in lecture, we also decided like something else we could do is we could just start counting like how many steps, you know, how many swaps are we doing, or like how many variable assignments does the algorithm do, or, you know, like how many pushbacks does it do? You know, like we could do that. That seems a little better than like measuring it with time, because like, you know, then it doesn't matter what computer I run it on. You know, I kind of counted the number of operations. Who thinks this is a better way to measure the performance of an algorithm? I have a couple of hands up. This is better, I would say. I also tell you guys that it is not always the case. So in industry, there are a lot of cases where it is better to just actually write it out and then measure how fast it is. So like, you know, it's a trade-off. You won't always use this method, but this is good for interviews, because in interviews, they're usually not going to ask you to like time your code. They're going to ask you how many operations does it take. Okay. And by my count, this does not count for bug bounty points. If I made an error here, this does not count. This is about how many variable assignments there are. 2n squared minus n minus 1. How many increments and decrement operations, how many comparisons. And then, you know, there's like other stuff in this algorithm. There's like, you know, you're comparing here, you're like shifting the vector to the right. You're like, there's a lot of stuff you're doing. So there's a lot of other things you could count. That's about how many there are. But to be honest, even I don't like counting each individual operation because it is very tedious and it takes a lot of work. Yeah, so a lot of work, very tedious. And to understand how long the algorithm runs, if I count each operation, then the next question I need to think about is, well, is it faster to add or multiply? What about assigning a variable? Like, which of these is faster than the other, right? And that, to be honest with you, does not really matter in the real world. So it's like, it should matter because you're like, all these little details make sense. But in the real world, I guess it depends on which real world. In the world where you're working with a lot of data, all these little details don't matter. Because what's going to matter is how quickly the algorithm, how many steps it takes, depending with the input size, and not very precisely. It's not even going to matter if it's 2n squared versus 5n squared, because that's just like, I can get a faster computer, and then it'll be, twice as fast. So it'll be, it'll go from 5 to 2.5n or something. So that's why we bring in big O notations. It's a meaningful way to talk about operations. So you're still counting operations, but it helps you ignore a lot of the details, right? And the way it helps to ignore this is that you focus on the behavior of the operations as n gets really big, okay? And again, like I said, in some cases in industry, it matters a lot for you to actually benchmark your code, right? So it's not always the case you want to do big O, but for interviews, they're going to ask you big O. But when you're actually working, like I've written benchmarks to see how fast my code is, and that's what matters. Because we're at the point where it's like, oh, it's not a better algorithm. I just need to figure out like, should I use standard shuffle or should I write my own way of shuffling a vector, right? Like, can I do better? Like, should I minus equals 1 or should I like equals variable minus 1? Like, which of these is, faster, right? But for our class, we will be focusing on asymptotic behavior, which just means what happens as n gets really, really large. And to give you guys a sense of this, here's a lot of functions. Hopefully this should be review for you. But FYI, this is n to about 1 million, okay? So for context, this is why like the only thing that matters is like the biggest exponent in your operation. Because it is not uncommon for you to have to sort 1 million integers. 1 million integers is actually not that many on a computer, right? It's like half a megabyte of data or something. Is like tiny, okay? So you actually do 1 million a lot of times, all the time. That's what computers are good for. If we were doing numbers like 50, I would just ask people to sort them or whatever. It's a lot cheaper than asking a computer. But if I'm doing 1 million or 2 million, then I need to ask a computer. And the problem with that is, for a constant time algorithm, it just means that it always takes the same amount of time, no matter what the input is. So that's super awesome. If you can get a constant time algorithm for sorting, you probably broke the world because that doesn't exist. So most likely you're wrong. But if you do think you have a constant algorithm for sorting, hit me up and we can publish a paper on that because we will be like awarded some sort of computer science prize. But the other thing is logarithmic. So I think we talked about this last time. Logarithmic really slowly. So if you have a logarithmic algorithm, that's really good. The logarithm of 1 million is about 20. The logarithm of 1 billion is about 30. The logarithm of 1 trillion is like 40. Okay, so you can get big, and it's still only going to take 40 steps. So that's why logarithmic algorithms are good. Linear are okay. N log n are pretty good. Like the n times log n of 1 billion is about 30 billion. So it's like not that great, but like, it's good. And then once you get into these are like okay, and these are like unusable. If you have an algorithm that's 2 to the n, this is called exponential. Even if you only have 1 million elements, this is more than the number of atoms in the universe or something crazy like that. So like the number, it's like not going to finish. Like if you have an exponential algorithm for sorting and I give you, 1 million digits to sort, you could get Google's supercomputers to run it. It will not finish before the heat death of the universe. right? It's like the universe will die and your algorithm will still be going trying to sort that list. Similarly, for like when you get to factorial, don't even talk to me. Like that will take like exponentially many heat deaths of the universe for like it to even get close to finishing. All right, so those algorithms, these are really terrible. We're going to cover some of these towards the end of the class, and then we're going to cover techniques to make them faster at the cost of correctness. So instead of being correct all the time, we're going to be like, well, maybe I just want to be right about 90% of the time. Can I then do it? All right. Yeah. So let's jump into Big O. Hopefully this is a little bit of review for you guys, a few examples. Can somebody like explain to me why each of these functions is this corresponding asymptotic Big O runtime? Yeah, back there. First one. Yeah. So you said you look at the biggest term. So here's the n squared. You ignore the constant and you ignore the multiplicative factor, right? So that's how you get O of n squared. Basically, a similar logic applies to the rest of these. So I'll just leave them up for the slides for you to reference later. Yeah. So walking through this in more detail, like why can we ignore each of these things? All right. So this constant factor usually depends a lot on which computer I'm running it. So if I'm running it on a really fast computer, this constant factor will be really small. If I'm running it on a slow computer, it'll be like 10, right? So we ignore it because we know that we could just get a faster computer to do the same algorithm. So we don't really care what that is. And then for these two, if you guys remember from calculus, the reason we ignore them is because we care about the case where n is big. So like we said, like once n gets to 1 million, this is going to be about 1 trillion. This is going to be 1 trillion. Yeah, this is going to be 1 trillion n squared. So 1 trillion plus 1 million is basically 1 trillion, right? So you ignore the rest of the terms, all right? So again, like pros and cons, I'll skip this slide. So this is the informal definition of Big O. So let's say we have two functions, T of n and G of n, right? We say that T of n is Big O of G of n, right? So this is n squared in our case, and this was like 2n squared plus 14n plus 5, right? It's just some complicated function. If T of n is at most some constant multiple of G of n. So we'll walk through an example step by step. So this is our T of n, and our claim is that this is Big O of n squared. So the tricks that you can use is you ignore the constant and you drop this constant, right? So that's how you get to the answer. But formally, why is this true? Like, why do we say it's Big O of n squared? If you graph both of these functions, this bottom one is x squared, this top one is 2x squared plus 10. You actually notice that this one's always bigger than this one, right? So it's not just that Big O tells you like, oh, my function is smaller than n squared. That is not what it does. What it does is it tells you that I can find a function that has a constant number times n squared that is always bigger than my function, T of n. And that's what, after some point, it's always bigger. So that's what we do here. So this is 3 of x squared. So this is x squared, this is 3 of x squared, and this is my T of n, which is 2 of n squared plus 10, right? And what you notice is that once n is bigger than 4, 3 times n squared is always bigger than my T of n. That's all Big O tells you. Big O tells you is there exists a constant that I can multiply n squared by. So for this Big O, there exists some number I can multiply n squared by, such that if I look into big enough n, this function is always going to be smaller than that function I found. All right. This is actually the formal definition. So you guys have done math. Are you guys familiar with these symbols? Some of them. Okay, so this is, if you haven't done math, that's fine. I will introduce you to them. It's okay if it looks a little scary or if you can't read it. Kind of like learning a new language. I don't know why mathematicians do this, but they like to come up with a lot of symbols for things that you can already say in English. So this symbol means if and only if. This symbol means there exists. It's a backwards E, okay? This symbol means such that, ST. And this symbol means for all. All right. So what is it? This is saying? This is saying I can say T of n is big O of some other function. Okay. So they're just two functions I'm comparing. So this is like, n is big O of n squared, or 2n plus 10 is big O of n squared. If and only if. So that means this part has to hold true. There exists a C and an N. So there exists two numbers such that for all n bigger than one of those numbers, n0, T of n is smaller than G of n times my constant. So there exists two such numbers where this holds true. That is the formal definition of big O. That is how you prove that something is big O of something else. All right. It has to fit this definition. And you guys just did this, or we just did this. So again, if we look at this, formally, what we did is we chose C equal to 3 and n sub 0 equal to 4. So we said, so how do I prove it? It says there exist these numbers. So I show you those numbers. I tell you what those numbers are. That's how you prove that this holds true. So I show you C is 3 and n is 4. If you plug those in, it says for all n greater than 4, so for all n greater than 4, T of n, which is this red line, right, is less than or equal to 3 times G of n, which is n squared. So that's what this is saying, right? So this is saying that for all numbers greater than 4, my red line is below my green line. Okay. Yeah, which is basically what we wrote here. 2 of n squared plus 10 is less than 3 of n squared, right? So that's formally what big O means. You can also choose other numbers. Those are not the only numbers you can choose. For example, you can choose C equal to 7 and n equal to 2. So there's a typo there. Let me fix that. This should be n equal to 2. Okay. So there is not a correct choice of C and N, but what you have to do is that there exists such numbers such that it's possible. So you have to find what those numbers could be. So as long as you have one example for this proof, then it works. All right. So again, like how fast this is, going back to insertion sort, it actually turns out that the running time is O of n squared. So again, if you are trying to count the operations, you essentially always get like 3n squared plus 5n, or like 11n squared plus whatever. So the running time of insertion sort is big O of n squared. Before we end lecture, I did want to check with you guys. I know a lot of this material, like I am trying to go a little deeper into more formal stuff that you guys hopefully have seen some of this before, but might not have gone as deeply into like the mathematical pieces of it. How do you guys feel about that? Either the pace, like did you guys follow along with what we were covering? Can I get, okay, I see some thumbs up for following along. Can I just get like a hands up if the pace was too slow today? Do you want me to move faster? Because I can always cover more content. Like I have there's a lot more stuff for you guys to learn if you want to move faster, like I promise. No? Okay, if the pace was too fast, anybody want to raise their hand? Maybe a little bit. I see a couple of people that may be a little bit too fast. Okay, well, I guess please like feel free to let me know if it's too fast or too slow. Do not be embarrassed. Like we will adjust the pace of the lecture as we go. Hopefully this was interesting to you guys. Again, like what you covered. Homework 1 is going to be released on Monday. This is going to be the first coding homework. So please start early. not for your sake. I hope it's going to be easy for you guys to do. I don't want the homeworks to be difficult and to like fail you, but it is the first time we're doing a coding homework. So I could have messed up with the instructions or with the setup. So if you start earlier, you can let me know, I can fix it. Yeah. Yeah, so that will all be included in the instructions when I release it. I am just writing them now, but to answer your question, all of the homeworks we submitted to Gradescope, including the code. So what you'll do is you'll download, what we're gonna use is we're gonna use Replit for you guys to get your starter code. And you can also edit on Replit. So you don't have to worry about like setting up C++ or like, this doesn't work on my computer. As long as you have access to the internet and a web browser, you should be able to run the code, change it, edit it, write your answer. And what I'm going to do is I'm going to ask you to download those files and upload them to Gradescope. Gradescope will automatically grade some of the solutions. So there will be an auto grader. I will let you submit as many times as you want. So you will know, at least for the coding portion, if you're getting all the points. So you can submit, and if you're not getting all the points, something's wrong with the algorithm. You should probably try to fix it, or maybe there's something wrong on my end. So you should email me either way, because maybe I messed up. All right. Last couple of announcements. No class, no lecture on Monday. And there is a couple of links. Somebody told me there's some sort of Splunk scholarship you guys should be applying to. I heard this from somebody from ACM. And then there's a CodePath like virtual career fair, if you guys want to check it out. Anyway, thank you for coming, and I'm still here.